We've made a lot of progress with the atom. We went from at the beginning of the 20th century to not really knowing that subatomic particles even existed, all the way to about the 1920s with all of these experiments and all of this knowledge being attained. So section 5 now takes all of that information and a few other things that we'll talk about in just a moment, and finally starts to put it all together in what we call quantum mechanics. Quantum mechanics is the term that we use to describe the structure and nature and behavior of the atom and all the subatomic particles inside. When we talk about electrons and all of the wonderful, crazy nuances of the electron, we realize that electrons have wave-like and particle-like properties. And if that's true, then the Heisenberg Uncertainty Principle states that we cannot know both the position and velocity or momentum of an electron at the exact same time. Because in order to determine the position of an electron, we would have to hit it with a photon of light to discover where it's at. But once we hit it with a photon of light, we've now changed its position and velocity. So it's impossible to know both of those things about an electron at the exact same time. An electron got pulled over by a cop. Cop said, "Do you know how fast you were going?" And he said, "No, but I know where I'm at." Sorry, I have to throw jokes in every now and then, especially when we're dealing with tough content like topic 3. So we get to the quantum mechanical model. The quantum mechanical model, or quantum mechanics, was actually developed by several great minds, but one of those people was Erwin Schrödinger, roughly in the 1920s, to describe the motion of subatomic particles, to describe basically all of this stuff and put it all together. The problem we had been running up to this point was scientists wanted to get concrete with the atom, and more so the electron, which does not behave in concrete ways. We were trying to devise a model of the atom that we could clearly see, that we could be able to describe exactly where all the electrons were. But we were coming up short every single time. So Erwin Schrödinger and his team basically decided, look, we're no longer going to try to describe the exact position of an electron. Instead, we're going to use mathematical equations, such like wave functions, in order to describe the probability of finding a particle such as an electron. I've got 2 videos linked on this slide right here, and they're also linked in your notes. I highly recommend watching these videos along with all the other videos that hopefully you've been watching up until now. The probability density map that we'll see in just a moment is the map of the most likely location of an electron. And we call this likely probable space an electron cloud, or more specifically, or more consistently, we'll call it an atomic orbital. So probability maps look different. There's lots of different types of orbitals that we'll see. We're going to see some orbitals that look like a sphere. We're going to see other orbitals that look kind of like a dumbbell or 2 balloons tied together. Orbitals come in all shapes and sizes, and we're going to see that in just a moment. But atomic orbitals are regions of highest probability of finding an electron. This region of high probability, like we said, is either called an electron cloud, or we're going to call it more so an atomic orbital. Regardless of what size or shape an atomic orbital comes in, the key thing I want you to get from this slide is that each atomic orbital can hold, at most, 2 electrons. It could be empty, it could hold 1 electron, it can hold 2 electrons, but it cannot hold any more than 2. With that comes the quantum numbers. The quantum numbers is one of those things where as we go through it, it might be a little confusing, and that's okay. The first time you go through it in this video, you may understand only a fraction of it. Let's say 10%. That's fine. When you watch the video I have linked here, you may understand a little bit more still. And when you start to see examples of how it's worked out, it'll make more and more sense. So finally, at the very end, it will just all click. So keep that in mind. But the quantum numbers are 4 sets of numbers that help describe different information about the orbitals that electrons can be in. The 4 quantum numbers that we're going to cover on the subsequent slides are N, L, M sub L, and M sub S. Now you may be saying, those aren't numbers, those are letters. I understand. Those are the labels. The n is going to be called the principal quantum number. The L is called the azimuthal or angular quantum number. Don't worry, you don't have to know that. We have the magnetic and then the spin. All four of those numbers are telling us something different. Think about it like this. Think about your address, right? Your address is composed of all different kinds of information. The number, the street, the direction, the city, the state, the zip code, the country, the planet, if you have some interplanetary pen pals, right? There's all these pieces of information that when we put them together describes a probability location of finding you. For example, if we put all the information into Google Earth about my address, it's going to pinpoint a probable location of finding me. Now, will I be at home? Maybe, maybe not. I might be in another region, but most likely that's the area you're going to find me. In the same way, these four things are like the parts of an address for an electron. Every single electron in an atom has its own set of the four quantum numbers. So, for example, if we were to take a look at a neon atom has 10 electrons. Every single one of those 10 electrons, every single one will have its own unique set of these four quantum numbers. And the four quantum numbers just tell us different information about the atomic orbital that electron is most likely found in. So keeping that in mind, this chart that you see on the screen here is a good Cliff's Notes chart. When we go through all four quantum numbers, come back to this screen and you can use this as a review. Where the numbers come in is going to be the possible values here, and we will cover that in each slide that we talk more specifically about each number. All right, so let's start with the first one, which is probably the easiest out of all four to understand, and that's the principal quantum number, which is n. What does it tell us? Well, first of all, n is also referred to as shells, but the thing is, n is going to tell us the distance the electron is from the nucleus. Remember how we said that there's the nucleus, and then there's the energy levels, n equals 1, n equals 2, n equals 3, and so on. So the n value is just simply telling us what energy level, or what orbit, or what shell the electron is living on. I kind of like to think of it like this. This is an analogy I'm going to use in the videos talking about quantum numbers. It's kind of like a hotel. So if we thought of a hotel, whoop, let me get my pen. Okay, so we have our hotel here, right? And you have different floors of the hotel. You have the ground floor, so first floor, second floor, third floor. That would be synonymous to what n is telling us. N is telling us what floor we are on. Now, what could be the possible values for n? N could be equal to 1, 2, 3, etc. Larger number is further away from the nucleus. The other thing is, remember, atoms aren't like a ladder. Atoms are instead like these shells or spherical shapes, right? So the more, think about it, the more energy levels that an atom has, the larger the atom is. So not only does it tell us the distance, but the more energy levels that an atom has, the larger the atom is. N typically corresponds to the row number in the periodic table. So, if I were to ask you, going back to our example of neon, what row number or period is neon in? Neon is in the second row. Because neon is in the second row, neon has two energy levels. It will have electrons in n equals 1 and n equals 2. Technically, neon has an infinite amount of energy levels, but the actual energy levels that will have electrons in them, it's just the two. What about if I asked you about magnesium? How many energy levels does magnesium have? Well, if we take a look at the periodic table, magnesium is in row 3, and therefore it will have 3 energy levels, n equals 1, n equals 2, and n equals 3. If we were to take a look at a picture, this just represents atoms of different energy levels. This first atom right here simply just has one energy level. Or maybe not, it's not a different atom, but this just represents the first energy level. Pretty tiny, right? This would show an example where you have the first energy level and then the second energy level gets a little larger. This would be where it has the 3 energy levels. Energy level 1, energy level 2, and then finally energy level 3. Now remember, electrons can't exist in between these energy levels. So that's where you start to see drops in between each transition. Electrons cannot exist in those areas. All right, let's go on to the second quantum number. So this gets a little weird. So n, in our hotel example, n was like our floors. What floor number are you on? Right? But what does L tell us? Well, L is not going to tell us the size or distance that the size or distance that the electron is. L is going to tell us the shape of the orbital that the electron exists in. L is kind of like room type. So maybe on the first floor of our hotel, there's only standard rooms. But if you go up to the second floor, you have standard rooms, as well as you have suites. And if you go up one more floor, now you have standard rooms, suites, and deluxe suites, and so on and so forth. The higher up you go, the more room types that there are. In the same way, the further out from the nucleus you go, or the higher shells you go, the different shapes of orbitals that you'll find. So L will tell us the shape of orbital. And there are 4 shapes you need to be familiar with. You need to be familiar with the S shape, the P shape, the D shape, and the F shape. They all have different shapes. Real quickly, I'm going to advance a few slides so you can see those shapes. Here would be your S shape. It is a spherical shape. The P shape looks like what we would call a dumbbell. I don't think that looks like a dumbbell. I think it looks like 2 balloons tied together, but that's what they call it. The D shape looks like a double dumbbell, or sometimes they'll say a clover. And then the F shape, honestly, F is just funky. It's weird. It's all kinds of weirdness. But all of those are different orbitals. And as a reminder, how many electrons can exist in each of those orbitals? 2. It doesn't matter if it looks like a simple sphere or this ridiculous crazy thing down here. All of those orbitals are atomic orbitals, and therefore they can only hold 2 electrons max. We'll come back to that in a moment, but the value of L will tell us what shape orbital we're looking at. If L equals 0, it's a sphere shape, S. If L equals 1, it's a P shape. If L equals 2, it'll be that clover shape, D, and if L equals 3, it'll be that funky F shape. So how do you figure out the value of L? Well, L always starts counting at 0, but it'll go all the way up to n minus 1. So what that means is this. Let's say if you were looking at energy level 3. Okay, I wanted to know on the 3rd energy level, the 3rd floor of our atom, what shapes are there? What room types are there? Well, I know L starts counting at 0, so I know that's where we start, but what do we go up to? Well, we go up to n minus 1. So if we're looking at the 3rd energy level, we go up to 3 minus 1, which is 2. So that means on the 3rd energy level, on the 3rd floor of the atom, there are L equals 0, L equals 1, and L equals 2 as all possible values, meaning there's an S shape, a P shape, and a D shape orbital all on that 3rd energy level. Let's look at that in a nice abbreviated or summarized way. If you're looking at the 1st energy level of the atom, the only L value that you could have is L equals 0. So the only shaped orbital that exists on the 1st energy level of any atom is the S shape. If you were looking at the 2nd energy level, the values of L you could have are 0 and 1, which correspond to the S and P shapes. If you were looking at the 3rd energy level, the L values could be 0, 1, and 2, which stand for the S, P, and D shapes. And finally, if you're looking at L equals 4, the allowed shapes could be L equals 0, 1, 2, and 3, which means you have all 4 shapes available. Now, theoretically, the shapes actually do keep increasing from that point, starting with leaving off where F was, going up by G, H, and so on. but we're only going to focus on these four shapes.